So let's continue our design parameters, how we can make this happen for your better design of seawater desalination plant. So what time is the best way to have a lunch today?
Yeah.
Now. All right. Okay, you can eat, that's fine. Or we can have official lunch time maybe 1 o'clock or anything like that. We can have maybe half an hour lunch is okay today? Yeah. 1 hour or 1 hour? Let's finish today lectures. So what's the terminology we have to use for designing desalination plant and recovery? Because recovery relates to your final concentration of remaining salt and your pure water. So we have to make sure recovery permeate over feed. So feed water is 1 kilometer per day. You want to produce 0.1 kilometer per day. So which means 0.1, like we have a recovery ratio, multiply by 100, so 50%. So you recover 50% because when you increase the recovery, you can reduce the energy cost, the operational cost. Why? You have a more problems, like the inorganic scaling problem, organic farming problem, or some scaling issues. So there are very, many problems occurring. So we have to set what's the best recovery for seawater. It's not only about seawater, but also wastewater. And what's the best recovery we can achieve from the optimization of better performance, no carbon issues, how we can negotiate this kind of recovery together. So seawater. So our seawater concentration in Australia, 3.5% of salt, right? How about other countries, other seawater, Indian Ocean, Atlantic Ocean, or Gulf, in Middle East area, Red Sea? What's the concentration of seawater? Same. That's wrong, because the Gulf area, Red Sea is a little bit close. But you can see that our Pacific Ocean is very open sea. So the concentration of Pacific Ocean is relatively similar, 3.5%. But in the Middle East, Gulf, Red Sea, 4.5%. So you have a higher concentration of salt because they have an evaporation rate is higher than dilution. Yeah. So you have to design when you have a higher concentration of salt. So 4.5%, your recovery has to be 35%, 40%. For seawater now in Australia, we have 3.5%. So recovery, you can go 45% or 50%. So you have a higher recovery, you will have a more efficient operation without any fouling issues, right? So how we can manage this recovery? So that's very important. Recovery is equal to permeate over feed. So you can decide depending on your salt concentration, also your inorganic scaling, your fouling issues. So in general, So when you design your seawater desalination plant based on your scenario, so we have 3.5% seawater, the recovery is 45% or 50% possible. So when you design what's the recovery you like to target, so you can just fix the 50%, then you can start design for your or 45%. Also, TMP, the transmembrane pressure. So when you have a membrane, so you pressurize your membrane, and what's happening is that you like to pressurize the chamber, yeah. Then you like to keep produce water. Then you have a fouling occupied holes. So you have fouling, then wood pressure has to be higher when you create a consistent flux. So that's exactly we are monitoring the transmembrane pressure. So we call TMP. So TMP will represent your overall the fouling impact. So we have to also look at the TMP carefully. Also, transmission is the exchange of certain salt across membrane. So we have to look at the detail, your concentration. So one of the assignment question is about boron concentration. So we have a boron, which is the harmful compound, and the seawater contains boron concentration 10 milligram per liter. So we like to reduce less than 0.5 milligram per liter. So what's the passage of certain salt across membrane? So you have to target, okay, this concentration less than 0.1, 0.5, 1 milligram per liter, TDS less than 500 milligram per liter. So we have drinking water guidelines in Australia. Yeah. So we have to make it sure all the water quality follow our Australian drinking guidelines. So you have to see. So this software will tell you which concentration, which compound you pass through this membrane, other membrane, so they can provide the information, or you will get 0.1 milligram of boron concentrations. You will get 100 milligram per liter of total dissolved solid. So you have all the information is available from our software. So you can see from your assignment, specifically look at the boron concentration in your seawater, and if this concentration is less than 0.5 milligram per liter, we need to make sure that not over this concentration. So how you can make sure this bigger concentration utilizing the high regenerative membrane, or second pass, or third pass, so you can improve overall individual compound. So that's the transmission. We have to look at it. Unit, the grouping of membrane, vessel, and pump piping. So when you design your assignment, okay, we like to design 250 billion liters per day. So we don't design 200 million liters per day together. So we just separate one unit. One unit, I want to design 10 million liters per day, or 1 billion liters per day. So when you design your assignment, so don't design all capacity 250 million liters per day. So you just separate small units. So that's exactly we are talking about grouping of membrane and pressure, vessel, pressure, module, element, with a common feed pump. So one unit has one feed pump to suppose 1 million liters per day and piping control. So you just multiply. Okay, I want to design 1 million liters per day with 1 unit. So multiply by 250. So you design total capacity of 250 million liters per day. So you don't have to go for whole capacity. Just yeah, you can divide by several units. Then you can design only simple one, like 1 million, 10 million liters per day, or 100, 150 million liters per day will be much more realistic and flexible design. But the element, so this is the element narrow. This is the one element. This is the nanofiltration arrow. One element we are saying this kind of this is module. So precision ultrafiltration. When they say module, it's individual membrane. So one module we have a very high surface area of your ultrafiltration membrane surface, which can calculate your overall water loss. So we need to design ultrafiltration as a module, and element is the reverse osmosis membrane. And cassette CIPA, cleaning in place. So you operate several months. So you have a cleaning requirement. So this cleaning, we just say CIPA. So how much chemical cleaning you have to go through when you have less than 70% of your overall flux decline. So you have to start your cleaning in place. The backwash. How to make the backwashing? So cleaning is required for reverse osmosis for element because you cannot backwash that because pore size is too small, so you cannot backwash the water the other way. But ultrafiltration, this is the membrane pore size is very big, so you have a keep producing water. Then you have a fouling accumulate on your surface, and the flux is keep increasing, and the transmembrane pressure is keep increasing. So in this case, you backwash, then detects your foulness on the fiber, then you just waste your backwash water and start again as your feed water, and you have a better water flux. So that's the backwashing. So backwashing is your precision ultrafiltration, microfiltration, large pore size can be applied for your. So when you design your assignment ultrafiltration, so you have to consider backwashing time. I want to operate 1 hour, then backwashing 1 minute. So that's how you can consider as a manual of your ultrafiltration, microfiltration membrane. Also, inert backwashing can be achieved with the different chemical dosing. Also, water quality. I'm sure that already you have very familiar with water quality, right? So I don't want to go through everything. We just want to look at what's the most important parameter for seawater desalination. Turbidity is important as a pre-treatment. Also, total organic carbon. So seawater does not have a very high concentration of organic compared to wastewater. Wastewater contains a lot of organics, which is the fouling membrane. So you have to think about total dissolved solid, not much in seawater desalination, and total suspended solid, iron, manganese, silicate, chlorine, temperature, oil. It's not really serious in seawater desalination design in water quality. But carbon dioxide bicarbonate is very important because they are combined with calcium carbonate, magnesium carbonate, magnesium sulfate. So we have to know what's the concentration of your company, right? Carbon. And acidity and alkalinity, hardness. Hardness is the calcium magnesium concentration. So you have a hard water, and this will create the more inorganic scaling. So what's the concentration? Phosphate. Also, dissolved solid is relevant to osmotic pressure. So osmotic pressure, we have to calculate your applied pressure. And then you can calculate your overall water flux. So how much water can be produced? So what's the osmotic pressure of seawater? What's the osmotic pressure of seawater? What's the applied pressure in seawater reverse osmosis?
Approximately 27.
Sorry?
Approximately 27 ATM.
27 bar, right? 27 ATM in seawater osmotic pressure. So you have a dissolved salt. So dissolved salt creates your osmotic pressure because of concentration gradient in between outer membrane. So you have seawater here. So you have a 28 bar of osmotic pressure. So you have membrane here, and then you have to apply pressure more than 28 bar. Otherwise, you cannot control your water molecule in this membrane. So 25, 8, and then 60 bar. So you pressurize 60 bar, 70 bar, and this will create your 50% of recovery because osmotic pressure 28 bar overcome osmotic pressure 60 bar, it's almost double. So you push your water molecule double, and then your brine, your concentrate become double as well. So which means your concentration of salt, osmotic pressure is around 60 bar. So you apply 60 bar, double concentrate, you have a same osmotic pressure, and then you will achieve 50% of recovery. So total dissolved solid is very important because you can calculate your overall applied pressure, how much water flux you can produce, how much water recovery you can achieve. So you have to see what's the total dissolved solid. Barium sulfate from disinfectant was an important parameter for seawater desalination plant. And this is the software. So some people have a problem to install this one. No one. So it's, it looks like this. You have a very good process diagram at the first screen. Then you can select your filtration process. And you can go next one. This is the feed water parameters. So you can see that all the detail. What's the individual compound of your seawater? So this is your relevant in your scenario. If you see the scenario shows your water quality individual concentration at the end of your scenario. So you just put your information inside your feed water, and then you will see what's the potential of scaling, what's the potential of your recovery, what's the membrane design. So we will learn this software tomorrow, how we can go one by one to design the different process. So this is very useful. You don't have to understand a lot of water chemistry. Even you don't have to think about manual calculation. Also, there are many element modules are involved, which you can manage through this software. And let's see. Seawater reverse osmosis. So who developed this membrane? RO, reverse osmosis membrane. First discovered 1965. At the time, they, tried to look at your textile. The membrane is originated from your textile and cloth. So you are wearing your cloth. So some clothes has a very nice pores, right? But some of the winter jackets, material is nylon, right? So this nylon looks like a no pore and you cannot penetrate any air, any water. Then they tested it. It looks like a very good barrier. Then they put into the cell, the pressurized 100 bar, 100 bar. And then there is something is going on. And they realize, oh, this one removed the salt. And we can separate water molecule and salt. So that's the reason why they started, okay, we can utilize membrane from our cross nylon material. Initially, it was our winter jacket nylon. They tested and they realized, oh, if we pressurize, we can separate water and salt. And they developed a better membrane. Now it's a lot of membrane determination points are very commercially available. So look at that. History. Initially, membrane competes with distillation. So you just boil the water, and then water evaporates, you desalinate it, right? Very cheap. At the time, the Saudi Arabia and Middle East countries, the oil price was very low. Yeah. So just to utilize oil to produce the desalinated water. So they initially utilized a lot of boiling water using oil or gas in the Middle East country from seawater. And at the time was cheaper than reverse osmosis membrane because reverse osmosis membrane require a little bit more better design. Also, you need to develop the material effectively. Also, pumping, high pressurized pumping was not available at the time. So it was 10 kilowatt hour for 1 kilometer. So as I mentioned, $0.3 per 1 kilowatt. So when you produce the 1 ton of desalinated water, you have to pay more than $3. Right? Only energy cost. So it was expensive than boiling water using oil. Oil does less than $0.1 and $1 for this energy cost. So price was much lower. But now it's the energy. Oil is very expensive, right? So you can see the oil price significantly increased. The distillation is no longer cost effective and reverse osmosis is more better because we can achieve 4 kilowatt hour of kilometer to bring water desalination with $1.2 1 kilometer. Because of pressure exchanger. The second innovation is first is more about the membrane, and we have more about the RO reverse osmosis membrane development. And then second one is the pressure exchanger. So we developed how to recover pressure. So like you recover heat. You have waste heat, then combined with the heat exchanger, so you observe the heat, and you can save a lot of energy. Same as the pressure. You pressurize after you pressurize RO. So leftover pressure you exchange again and apply again at the RO pressure exchange. So pressure exchange was developed 1990s. And we decreased energy cost more than 50%, which means now it's around 2 kilowatt hour per cubic meter. So second innovation, pressure exchanger. So we discovered 30 years ago. Since then, we utilized this membrane reverse osmosis technology for most cost-effective desalination process. That's why I don't want to talk about this because it's more expensive. Also, process is relatively simple, so that it's a little bit traditional. Of course, this technology is also some opportunity to utilize, but in general, in our class, the reverse osmosis is the most powerful. Also, it can be used for wastewater reuse, reverse osmosis. So it's like all gold standard of water treatment, water desalination, wastewater reuse. So that if you are very confident for this one, you will be very familiar with designing the water treatment process. So let's learn about our membrane. The water molecule 0.3 nanometer. We have to separate water molecule and sodium chloride. So this membrane is very small pore. And you can separate metal, sodium chloride, the different range of your atomic level of. So we just say non-porous membrane. Ultrafiltration is porous membrane. So it has pore, and then water molecule easily possible. So it's very porous membrane. But reverse osmosis, there is no pore. It's like a non-porous membrane. So they have a membrane thickness increase, permeable flux increase, active layer. We just say active layer. At the behind, you have support layer. The active layer separate your water and salt. Support layer support your pressure because the pressure is 60 bar. So pressure is very high. So if you don't have a good support layer, so your active layer polymer will be easily break down. So active layer as thin as possible. But if your active layer is very thick, very difficult to pass through water molecule. So you have to pressurize a lot. So they want to make it as thin as possible. Yeah, that's the how you can produce the more good membrane. So membrane structure asymmetric, asymmetric. So you have a very thin layer, active layer, at the behind support layer. So we just say asymmetric structure, and since we compare it for nanofiltration RO membrane, we can utilize this one. So it looks like this. So if you make a microscope image for this cross section, so you can see how it looks like. So on the top, so there is a thin dense skin layer. So this is the thin dense skin layer here. And you have a polysulfone layer. And you have also a backing layer. So membrane, this one has 3 layers. So you have a separation of a water molecule and salt from this active layer. The familiar, your material is nylon. Nylon is the main component, but it's not same as what we have our cross of nylon. It's specifically also designed. And this is the polysulfone backing layer. The skin layer is at 20 nanometers. So we separate the water with the 20 nanometer of active layer for seawater desalination. So how this works? So let's see how this membrane is fabricating and how it looks like.
To create our standard spiral wound membranes, we construct the flat sheet membrane using hydronautics automated casting equipment. We begin the process with a fabric support base and then coat it with a microporous polysulfone layer. This provides additional support for the top 0.2 micron thick membrane barrier layer. This top barrier layer makes the actual separation to purify the water. The semi-permeable polyamide layer consists of a thin film of polymeric material a few thousand angstroms thick, formed on a porous supporting material. Semi-permeable membrane skin is formed on the polysulfone substrate by interfacial polymerization of monomers containing amine and carboxylic acid chloride functional groups. Hydronautics manufacturing procedure enables independent optimization of the distinct properties of the membrane support and fault-rejected skin. The combination of these three layers makes a durable membrane flat sheet that is used in each spiral wound element. The membrane flat sheet is then combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets to allow uniform flow of the water to the entire membrane surface. The leaves of membrane and feed channel spacer are then combined with a sheet of permeate spacer, which provides open flow channels that will permeate even under high pressure. The leaves are glued along each of the three exposed sides and then rolled around the core tube. With the back of the membrane completely sealed to the edges of the permeate spacer, the feed water is forced through the feed channel spacer, contacting the front or barrier layer of the membrane. Clean water, or permeate, passes through the membrane surface into the permeate channel and then flows in a spiral direction to the center of the element and is collected into the core tube. Hydronautic spiral wound elements can then be loaded into pressure vessels and interconnected with additional elements to complete any number of design specifications. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced and then treated. The feed water that does not permeate through the membrane becomes enriched in salts as it travels through the feed channel spacer due to permeate water being removed. Typically, 8 to 10% of the water is removed in one 40-inch long membrane element. The permeate water then flows out the end of the vessel and is collected as the product. And the reject or concentrate from that vessel may then flow through another vessel producing more permeate. The remaining concentrate may then be disposed of as waste or partially recycled as the feed. Typically, 70 to 90% of the water can be recovered as pure product water.
So this is the reductive rolled element. So we have a support layer, spacer, membrane. The water is just pass through the spacer here, and then slowly you desalinate your water, and you can achieve 50%. So you need one element, 10% recovery. Another one is 20%, 30%, 40%. Also, your salt concentration keep increasing because you are desalinated water. So your seawater is salt concentration is keep increasing, so keep changing. So your flux is keep decreasing. So each element, initial staging, osmotic pressure different, salt concentration is different. So you recover one module, maybe 10%, another one 7%. Yeah. So it takes several modules you have to go through to achieve final recovery 50%. So that's exactly what we need to design. Yeah, one by one. So you need to think about osmotic pressure, you need to think about your cloud, you need to think about your brine concentration change. Yeah. So you have to calculate all the detail and then finally you can design. Oh, I need a 100 element. I need a 1,000 element. So you need also pressure buffer, how many elements you can allocate. So that's exactly your assignment. Calculate your design 450 million liters per day and how many elements you need, how many pressure vessels you need, how many pumps you need, how many frame you need, how many units you need to look at all the details. So that's we have to look at detail how we can calculate this kind of informations. So we have to understand transport phenomenon, how we can calculate diffusion, osmosis, concentration, polarization, and permeate flux. So this is all interact each other to calculate over your design outcomes. So let's think about first osmotic pressure. Already we briefly mentioned about this one. So osmotic pressure is feed water brine. So you have a feed water here brine, and you have a feed water pure water. And because of concentration change, so membrane is here, and your water molecule pass through the high concentration of your brine side, and then you increase the overall volume. So that's exactly we just say reverse osmosis, forward osmosis, osmotic pressure. So forward osmosis, just to use osmotic pressure is forward osmosis. Reverse osmosis from brine to feed side. So you just push reverse way, and then water molecule goes to the reverse side. So we just say reverse osmosis, outer membrane. So let's look at the nature. So we have cherry here. So when time comes, so you have to take all the cherries, but you got a rainfall and rainwater, even though it was enough to have a good, take the farm this cherry, and you will break down your cherry a lot because of rainwater. You can see the cherry has skin. So this skin is same as our skin, natural bio membrane. So this membrane, inside the cherry, you have sugar. The sugar has a high osmotic pressure. And then your rainwater is flowing through the surface of cherry, like this way. And quickly, your cherry skin, as a membrane, you have a sugar inside your cherry. Osmotically, they are sucking your water molecule. And it keeps swallowed and swallowed, yep. And then finally it's break down your cherry. So it's the same as osmotic pressure we can see from our nature. So sodium chloride, when you have a seawater, 35 gram per liter, osmotic pressure is around 27 bar. And sodium chloride, 1 gram per liter, 100 kilopascal, 1 bar. So depending on your concentration, you can calculate your osmotic pressure. This will reflect your overall recovery and osmotic pressure and applied pressure. So magnesium sulfate, even though it's same as concentration 1000 milligram per liter, osmotic pressure is lower. And sucrose, like a sugar is 1000 milligram per liter, same concentration. Osmotic pressure is much lower. So which means what happened for this osmotic pressure? So when you have a different ions, different organics, inorganics, it shows the different osmotic pressure. So how we can calculate this one? That's the exactly I mentioned about Bandt Hoff. I'm sure that you already heard about this equation. So he got the Nobel Prize because of this equation. The osmotic pressure is equal to CLT, the concentration of each ion, and then ideal gas constant, and then temperature.
So less osmotic pressure means there is less movement of, because there is not much osmotic
No.
pressure there, so there
It's
is no.
not, it doesn't mean less osmotic pressure means not less movement. It's that's exactly, osmotic pressure is concentration. So what concentration you have, and the ideal constant is fixed, and temperature. So it depending on what's the concentration and what's the temperature. So when you increase the temperature, your osmotic pressure increase because your concentration is dissolved better. So you can calculate your osmotic pressure from concentration and your ionized form. So we have to careful dissociated solute. For example, sodium chloride, yeah. Sodium chloride has two dissociated solute. So sodium chloride, so you have two ions, right? So concentration multiplied by two ions, right? But when you think about magnesium 2 plus and magnesium chloride, MgCl2, so magnesium and Cl2, chloride minus 2. So they dissociated Mg1, 2 chloride. So 3 ions. So dissociated solutes are 3, which means you have to multiply by 3. So how many ions individual dissolved solute you have? It affects your osmotic pressure. So you can calculate based on this equation, and this will impact your overall calculation of osmotic pressure. But as I mentioned, the seawater has more than 1000 elements, right? So how we can calculate every single element, like a sodium, high the CLT, sodium concentration, RT, chloride, and chloride concentration multiply RT. We have a lithium, magnesium, calcium, silica, any of a component, you have to calculate each concentration, R, and temperature, and then this dissociated solid. So you have to calculate each individual and then get the osmotic pressure. So it's very difficult to look at all the details. So we just make a rough calculation of total dissolved solid. So TDS reflect. So what's the TDS, total dissolved solid? 35 gram per liter is equivalent to 28 bar osmotic pressure. To make it very simple, because we have a conductivity method, TDS method, and you can easily measure in a very simple way. And this can convert. You have a 35 gram per liter equal to 28 bar of osmotic pressure in seawater. But some seawater, as I mentioned, the Middle East country, Red Sea or Gulf, they have 45 gram per liter. So osmotic pressure will increase up to 35 bar. Yeah. So they have a change of different TDS concentration, and easily you can convert to osmotic pressure, and you can calculate. So 28 bar, 35 bar, 40 bar, depending on that, I want to achieve 50% recovery rate. So your osmotic pressure is 40 bar. So you have to apply 80 bar pressure to achieve your overall 50% of recovery. So this osmotic pressure will tell you how much pressure you apply and how much you will get recovery and how much water you will receive. So osmotic pressure is very important, and we have to know about what's the osmotic pressure relationship from the feed water and permeate, and you achieve the 0.5, 50% recovery, and this is the around the 3.5 kilowatt of a cubic meter. Energy consumption, theoretically, we calculate, and it's only very small, 3 times lower. But because of the practical point of view, our membrane is not perfect. And then we have also some other problem, concentration polarization. Osmotic pressure is 37 bar in seawater. But what happens is you have a concentration polarization. The salt concentration at the membrane surface is higher than bulk. So you have a seawater 28 bar osmotic pressure, concentration is 3.5%. But you pressurize, so your ion accumulate on the surface of membrane, which means your polarization is occurring on the membrane surface. Your concentration is high, which means you have a high osmotic pressure on the surface. So diffusion from the membrane surface back to the bulk solution, back diffusion can be enhanced by cross flow. So when you see theoretical calculation, but the real application, you have to calculate concentration, polarization, osmotic pressure on the surface of membrane to see the real osmotic pressure between you have a permeate, you have membrane, your seawater concentration is 3.5% here. But on the surface, because you're pressurizing, the water molecule is passing through membrane. So you have accumulation of salt on the surface of membrane. So this concentration polarization will further increase your overall osmotic pressure. So how we can calculate this one? So that's exactly also different from the theoretical, our energy consumption, and then practical energy consumption. And this is element, so what kind of membrane standard we have to use? The BW4040, SW2540. So you need to select from the software, the BW48, 4040, 8040. So which one is the best selection of your membrane module, membrane element? So what's the meaning of this one is brackish water 40-inch and 4-inch in diameter and 40-inch in length. So you have a 4" and 40" in length. So 40" is almost 1 meter. Yeah. And then 4" is almost 5 centimeter. So you have a 8" diameter, 10 centimeter, 10 centimeter of your spiral of the module. The length is 1 meter. And then what's the surface area of this membrane? So you can calculate what kind of membrane standard we have to utilize from this one. And we can think about what's the good compatibility of pressure vessel, simple design, R&D benefit, also lack of diversity of like the same as Apple. Apple like different power supply system, and Samsung, they have a USB-C type of power supply system. Same as membrane module and pressure vessel. So if you have a different company, different pressure vessel, pressure element, pressure, yeah. So everybody cannot buy each other. I like to have a this size of diameter, but the pressure vessel cannot fit with 10 centimeter or 5 centimeter. Different company, they try to make a difference. So luckily, our membrane business is better collaboration than mobile phone. So they have a standard 10 centimeter pressure vessel, 5 centimeter pressure vessel. So we can buy any of the different company membrane module with the standard of diameter. The length is also 1 meter. So they also fixed okay, let's make 1 meter of element. So every element, so relatively they are similar size of length, 1 meter. So we can utilize any kind of company. We can buy this standardized your element. So you can compare the result because every member has different performance. Some of them they work better, some of them they work less, some of them specifically better removal of this compound, some of them better removal of this compound. So we have more than 500 our membrane in the world. So you can select any of the membrane. So in the software, so that's why you can select. There are around 25 membrane elements from the Wave software. So you can select, okay, I like to do SWR for our design. Okay, this membrane is best for me. So you can pick up the one of the membrane module type and you can calculate from your design. So that's how it works. Let's see how the membrane module element are producing from the membrane company.
FilmTech Corporation, a subsidiary of the Dow Chemical, is the world's leading manufacturer of reverse osmosis nanofiltration membranes. Our products are used in a wide variety of industrial, municipal, residential, and commercial applications, helping Dow achieve its mission of improving what is most important in life, the human element. Our cutting-edge manufacturing technology improves the performance and quality of our membranes and provides the scale and infrastructure to serve the rapidly growing demand for RO and NF membranes. Providing high-quality membrane products starts with quality raw materials from ISO-certified suppliers. FT30 thin film composite membrane, invented by FilmTech nearly 3 decades ago, is the genesis of today's industry standard. With each new generation of manufacturing equipment, the quality of FilmTech membranes is continuously improved through advanced process automation and control, from handling polyester-based material through casting the microporous polysulfone support to the complex polymerization reaction that creates the polyamide membrane layer. Design innovations allow us to use advanced membrane recipes that improve membrane performance and consistency. Dozens of critical variables are controlled and inline quality checks are performed to produce consistent, defect-free membrane without patching, and giving Film Tech membrane the widest pH cleaning range in the industry. A spiral wound membrane element can be fabricated manually or automatically. Dow uses custom-designed precision rolling equipment to automatically fabricate Film Tech elements because it allows for better, more consistent element performance. Sophisticated robotics for leaf construction and assembly ensure that every element is precisely built without membrane damage that often occurs during manual handling. Automation enables construction of more shorter leaves compared to manual rolling, resulting in a more efficient product that is less prone to fouling. Precise computer-controlled glue lines ensure the highest active area in the industry with guaranteed accuracy and minimize leaks, which can result in poor permeate quality. Film Tech elements are optimized to have the highest active area combined with the thickest feed spacer in the industry, offering several operating benefits, including improved cleanability, lower pressure drop, increased durability, and the ability to handle more challenging feed waters. A unique barcode allows continuous tracking of each element. Online quality checks for scroll integrity and dimensions and an inline vacuum test are performed on every element to ensure mechanical integrity. Any elements failing preset measurements are discarded. End caps are welded to the product water tube in a process that improves element strength, and a quality test ensures weld integrity. Our automated fiberglass process ensures exact and uniform fiberglass application within controlled dimensional tolerances. To validate final element performance, Film Tech uses both a traditional 20-minute performance test and a groundbreaking pulse integrity test, which has the unique ability to detect and diagnose mechanical defects. Tests are computer controlled, and elements not meeting defined test ranges are discarded. Custom designed packaging equipment combined with precision injected preservative ensure protection for elements during storage and transportation and easy handling. Prior to shipment, product for each customer order is scanned for traceability and to validate all previous quality checks. Quality is built into every Film Tech element, from the management of raw materials to final shipment. Every element undergoes multiple inline quality measurements, and additional parameters are measured based on defined sampling plans. Our technology enables a robust, consistent, defect-free membrane with the industry's widest pH cleaning range. Automated precision fabrication enables elements with maximum guaranteed active area, the industry's widest feed spacer, shorter membrane beams, consistent high-integrity construction, and eyelet interlocking end caps. Collectively, these features enable consistent, reliable performance of RO systems with reduced system capital and operating costs. With the infrastructure to meet the rapidly growing demands of the market and the technology framework for integrating future innovations, Dow continues to lead the industry in reverse osmosis performance and value enhancement. Our goal is to offer the best membranes to enable the highest quality water at the lowest total cost. Innovation, automation, quality, Film Tech.
So they are producing this kind of element out of membrane, 1 meter length, 10 centimeter of diameter. So you need to design for your assignment. You don't have to worry about different water, different size. Just fix 8 inch, 10 centimeter of diameter, and 1 meter of length. So then you can see that exactly same line. So how much this worth? One element. $100. Anybody? $500. So how many do you need? So for example, this 60 watt in Sydney. So how many we need this element? 1 meter 10,000. That's exactly your size. You have to figure it out. How many elements we have to see. It depends on the surface area. The one element contains 20 square meter of membrane surface area. How much water flow you can obtain? How many elements you need for producing 250,000 cubic meter per day? Right. Yeah. And you know how much you require for element. That's how you can think about design, edition, cost estimation, kind of investment. So that's your final. Second question. How many within this model? Pressure buster really, if you include the cost analysis, very much detailed. Design report, you can make it. So after we design this element, let's go for more detail. Nanofiltration, reverse osmosis. We have an element already inside. 3 elements. So you need to cover with the pressure vessel. The pressure vessel consists of fiberglass or stainless steel, up to 8 spiral round elements in a vessel. So you have to also design for your assignment. How many elements you want to allocate in your pressure vessel? 1 pressure vessel, you can put possibly 8 or 7. So you can fix, okay, I want to put 1 pressure vessel, 7 element or 8 element. And buses can be arranged into banks and desired number of stage and passes. So that's how you can calculate how many elements you have, how many buses you need, and then that's you have to consider carefully. And this is the spiral round, very typical way of pressure vessel. So 1, 2, 3, 4, 5, 6, 7 elements are inside 1 pressure vessel. So we have a flux distribution. You have a higher osmotic pressure increase. And then you have a low water flux. Pressure will be lost. Initial stage, for example, like you have a seawater goes to here. Yep. And then you keep concentrate your feed water, and pressure is keep losing and losing, so that pressure loss will be there at the end of your pressure vessel. Initially, you pressurize the 60 bar, and you are losing little by little, and then finally, at the end of this pressure vessel, you may have 50 something pressure, depending on your membrane flux. So you have to also consider, because flux reflects to your overall pressure and then concentration calculation. So how we can calculate this one? So that's another consideration we have to see. Even you have an element, 8 element. When you have a salinity TDS, the first element, the concentration is low relatively compared to the last element. So your permeate, total dissolved solid, is lower than last element, because last element has a high concentration of your salt. Then you pass through the more salt. So you can see the already more than 2 times higher your salt concentration, which means your final product, you need to calculate, combine all the water permeate, how much concentration we need to design. Also, individual ion like a boron, how we can reduce our trigger concentration of boron. So if concentration is higher after this permeate, okay, you want to go second pass. That's how you have to design different way of your individual concentration permeate design. Also, you can see the permeate flux. Initially, your permeate flux fraction is you produce the water 25% from the first element. But at the last element, you have a less than 5% of overall permeate flux, which means you have a high concentration, you have a high loading of fouling at the end of the element. High concentration polarization will create the overall less permeate flux. So this is all combined. So you design your element, which means you design only one element. You have to consider all modules, all facial vessels, depending on their change of the pressure, concentration, permeate flux. Can you calculate one by one? For 250 billion liters per day, that's what it is. We don't want to go for individual calculators, so we have to utilize our software that understand rather than we calculate all the change and the variation and all the consideration of flux, concentration, osmotic pressure, concentration, polarization. So that we have to utilize a smart way to go for our overall flux.
Professor?
Yeah.
So in a pressure vessel, there are 7 elements.
Yeah.
And every element is subjected to different osmotic pressure,
Yes.
different concentration.
Yes.
So the rate of fouling and scaling will be different for
Yes.
every element.
Yes.
So
That's exactly depending on the pre-treatment. So we need to design the pre-treatment carefully. When you have water filtration, pre-treatment, directly, you have a good quality of clean water to RO. But when you have a pure media filter, still larger particles will pass through your filtration compared to the ultrafiltration membrane. So you have a more high fouling tendency. So it shows the different treatment will consider your RO, but it's another weaker point of our RO membrane software. They cannot see the detailed fouling potential. So it's like more about the experience based. Okay, you have this level of flux. Theoretical, this is software is a theoretical flux and calculation, but the real consideration, okay, always there are some contaminant which create the overall flux. So you have to consider factors. Same as you have a new membrane. You have a very good performance. 1 year later, reduce the 10%. 2 years later, performance reduce 30%. So same as this kind, but unfortunately, this software cannot calculate all this kind of detailed fouling potential as well as aging impact.
and so if my pressure vessel is failing, so do I need to change the entire vessel or just the last module, last element, we can change that?
Last sentence first. That's exactly I want to show you in this next slide.
Well, it's like the last bring out the higher chance of falling? Oh, yeah.
Cold. I will show you this one in this slide. Yeah, this one. So why is the last one is high speed power potential. Inside water, so there are many different materials, organics, or ions. So when the it was start from the initial stage, so you can see that's colloidal organic power. Because organic and colloidal depressurize and easily attached on the initial membrane. So you have a lot of colloidal organic power at the initial level. And you have a high concentration of inorganic, like hydrogen manganese. You have a double, your pure water is keep produced. Then you have a brine. Then at the end of your element, so there are a lot of inorganic compounds, very high concentration compared to the first stage. Last stage, your calcium concentration is double, sodium concentration is double, even silica concentration is double. So they have a combined together and then start to precipitate because of high concentration. You produce more water, concentrate your pure water. Inorganic fouling. So it is silica, calcium, magnesium, inorganic fouling will occur at the end of your element because of high concentration. It makes sense?
Alright, by double, do you use like a ratio of like the water, because like the further it goes, like the less water like goes through, or like how does it double the number?
Double, okay.
Yeah.
Okay, let's say calcium, you have calcium concentrated. The initial will go 1 milligram per liter. And then water is keep penetrating. Pure water is passing through membrane, right? So you have a pure water, but this one is only remove the water, and then you have a relatively, it's not really increasing your beer content, but your concentration within water. You're saying what that? Yeah.
So what, okay,
Yes.
so the water that goes through the last membrane is the brine, not the,
Right.
not the
Yes,
Uh,
right.
permanent, the filter.
Permeate is the
Oh, so that's why, okay, I get it, thank you.
so that's the how they are creating the problem of the overall membrane fouling and then change the water flux. That's a good question because the problem is in your software you cannot calculate this one because depending on your water quality, depending on your pretreatment, depending on the also temperature, depending on the recovery, so you cannot perfectly calculate this one, but at least we can consider similar pattern of our design of this fouling impact. So if you try your software, you will see, okay, you have a very strong inorganic fouling, solubility is too high, calcium carbonate, calcium sulfate. So they are the major initial inorganic fouling is CO2 desalination. So calcium carbonate, calcium sulfate, magnesium carbonate, magnesium sulfate. These are the main inorganic scaling at the end of the stage. So we just look at carefully concentration and recovery impact. So now we are okay, 1 o'clock already. So we will have a lunch and come back around 2 o'clock. So we can start 2 and we can continue what we have to design for your seawater desalination plant. Okay, have a nice lunch.
You also can answer in the example.
Just want to clarify something.
Second.